A very good morning to you. Today, June the 2nd, 2020, is the third meeting of Chemistry Society this term. Today I'm going to talk about the chemistry of manganese and iron. When I was 10 years old, I used to live in West London in Shepherd's Bush. And every Saturday afternoon, I used to go to Shepherd's Bush Market. You see, I was very keen to see what people were buying, what they were selling, but most importantly, what they were throwing away. Because frequently, among other people's rubbish, I could find something useful for myself. For instance, a wooden box from which I could make a cricket bat. But every Saturday afternoon at Shepherd's Bush Market, there was a very strange man. He was selling medicine. He was selling medicine in the form of large green tablets like this. And he told everyone that this medicine was the best medicine in the world. It could cure you of any problem which you might have, whether you had a headache, toothache, migraine, muscle pain, rheumatism, neuralgia, even nostalgia. This would cure your problem, he said. And the reason why, he argued, is because unlike many other medicines, this does not contain any acid. And everyone knows that acids burn. Now, to prove his point, he had some examples of medicines which contain acids. He had, for instance, a tin of Seidlitz powders. Now, those were used to treat constipation. He read the label on the side. They contain tartaric acid. Acids burn, he would say. And then he had a tin of Andrew's liver salts. These are used to treat indigestion. He read the label on the side. These contain citric acid. Acids burn, he would repeat. And then he had some aspirins, a bottle of aspirins used for treating headaches, migraines, toothaches, etc. He read the label on the side. These contain acetyl salicylic acid. Rather than telling you what this can do in your stomach, he said, I am going to show you. So people were intrigued. What is it that he was going to show them about this dreadful medicine which contains an acid? He placed 2 aspirin tablets on the palm of his hand. And then on a large tin lid, which he had every Saturday afternoon, a tin plate, he placed them on top of some very dark crystals. And then he said, when you are suffering from a headache or a toothache, it is possible that you may also have a sore throat, in which case you might like to take some cough syrup. And he then pulled out a bottle of Sanatogen baby cough syrup, and he poured some cough syrup on. And then he said, when you have taken these medicines, you might not like their taste, in which case you might take a drink of water. So he sprinkled a few drops of water. He put a few drops of water like that. And then he said, watch carefully, because in the next few seconds, you're going to see how this horrendous medicine containing an acid can burn a hole in your stomach. Now, as people watched, the whole thing suddenly burst into flames, as you just saw, and people were absolutely terrified. And you know what they did? They said to themselves, I don't want to have that happening in my stomach. So do you know what they did? They started fumbling and bumbling around in their pockets until they found one of these. Now this is 2 shillings and 6pence, half a crown. It's a huge amount of money. And every Saturday afternoon at Shepherd's Bush Market, everyone used to buy the magic medicine man's magic medicine. Now I have to tell you that when I was 10 years old, I was very lucky because I was never ill. Furthermore, I had no money so I couldn't buy the stuff in any case. But I also have to tell you that ever since I had been a tiny baby, I had developed a serious psychological malfunction. And that means I had developed a secret and passionate obsession with fire. Now, my parents had bought me a chemistry set when I was 8 years old. I have it here to show you. I have the chemistry set here to show you. This is the exact chemistry set which my parents bought me when I was 5 years old. And I was very excited. I used to mix all the chemicals together in an attempt to make fire, obviously. But all I succeeded in making was fizzes, pops and smells and colour changes. Nothing like the magic medicine man at Shepherd's Bush Market. So I decided I would try to repeat his experiment. Now, I knew where I could get the aspirins from. They came from Boots the Chemist in Uxbridge Road. I knew where I could get the Sanatogen baby cough syrup from. That too came from Boots the Chemist in Uxbridge Road. I knew where I could get the water from. It came from the tap. But what I didn't know was the identity of those purple crystals. So I decided to find out. I went along to Shepherd's Bush Library, and there I borrowed a book which was called Chemistry Magic. And here is the book. I've actually got a copy to show you. And this is the book. This is the exact book which I borrowed. It's the same book. And in this book, I started reading about all the recipes that I used for making firework mixtures, pyrotechnic mixtures, to see whether there was an ingredient in fireworks mixtures which resembled those dark purple crystals which the man used at Shepherd's Bush Market. And do you know what? There was such an ingredient. It was called potassium permanganate. So together with the other substances, the medicines, I procured some of the aspirins, the cough syrup. I procured some potassium permanganate. I set up the experiment in my mother's kitchen at 44 Stanley Road, Shepherd's Bush, London, W12, and lo and behold, within 30 seconds, the whole thing burst into flames and filled the entire kitchen with smoke, just as I have done today. And do you know what? That was the greatest moment of my life, for that was my first ever truly successful chemistry experiment. And ever since that day, I have been conducting chemistry experiments on an everyday basis. But today, I thought I would tell you about this substance, potassium permanganate, which has turned out to be a most fascinating substance indeed. And what I've done, the first thing I noticed about it in the very early days of my chemical learning was how an intensely deep purple solution it could make. I have never come across a substance to this day which makes such a deep colored solution in purple or in any color as potassium permanganate. So what I thought, I would start off today just by showing you how we can make solutions of this more dilute, and to investigate to see how dilute we can make potassium permanganate solution before we can't see the color any longer. Now, for this purpose, I'm just going to rearrange my apparatus a little bit. I'm going to take off my steel mat here. I'm going to remove my brick, which I had to protect obviously protect my table. And I'm going to introduce you or show you these 6 flasks which I have here. 1, 2, 3, 4, 5, 6. We'll bring them right to the front here for you all to be able to see. And at this stage, I wanted just to tell you about this solution which I have in here. You see, this solution of potassium permanganate I have in here is a saturated solution. It contains as much dissolved potassium permanganate as you can possibly get into this volume of liquid. Now, the definition which I learnt at school, I was at Latimer Upper in 1963, and my teacher was Mr. Clive Burrow. We used to call him Bunny. He was a brilliant chemistry teacher, fantastic experiments every lesson. And Bunny taught us the definition of a saturated solution. And here it is. A saturated solution is a solution in which the dissolved and undissolved solutes are in equilibrium at the temperature under consideration. Now, when I learnt that at the age of 13, I didn't have a clue what it meant. It was just mumbo jumbo. But today, you see, I can explain to you and show you exactly what is meant. You see, the solute, obviously, is potassium permanganate. That's what we've dissolved in the water. We have made a solution. Now, what about this dissolved and undissolved bit? Well, you see, the dissolved potassium permanganate has made, this has been, by the way, standing for 24 hours. I made this up 24 hours ago. And it has, what we say, reached equilibrium. The temperature in this room, I measured it, it's 21 degrees centigrade. There's my thermometer. It's been constant ever since last night when I made this solution up. And if I put my spatula in here and I swirl it around on the bottom, then you could see some solid has come out. Now that solid, you see, won't dissolve. And what we say in chemical terms is that that's an equilibrium situation, because the temperature is constant, no more will dissolve and no more will be precipitated out as in the form of crystals as the solution exists. So that then is what we call a saturated solution. It's one you can always recognize a saturated solution because there will, if it's been standing around for a while, because there will be crystals of the solute at the bottom. In this case, we can't see them, so I've drawn them out to show you. So this is a saturated solution. By the way, I've looked up what the solubility of potassium permanganate. It's at 21 degrees centigrade. It's about 52 grams per litre. Now, 52 grams per litre is approximately a third of a mole. The formula mass of potassium permanganate is 158, so 52 is approximately a third. So it's a solution, the concentration of this is about 0.33 m, 0.33 molar. So what I'm going to do is this. I am going to successively dilute this solution down by a factor of 10, and we'll see how long we can observe the color for. Now, if you don't mind, I'm going to first of all just clean off my very, very, very dark purple spatula and put that to one side, since I won't be requiring it for this any longer. Just put it down here. And then I shall syringe out. Now, I've got a syringe here. It's got a tiny bit of plastic on the end, but the honest truth is otherwise I wouldn't be able to reach in it. So this is not a super accurate experiment, but nevertheless, it should demonstrate the principle of dilution. So I'm taking out 10 milliliters of my saturated solution there. I am now going to squirt it. Now this is 90 centimeters cubed of water. So I'm squirting it into there, you see, there it is, 90 cc's of water. Now it's been topped up to 100. So we've diluted it by a factor of 10. We now put our syringe in again, suck up, draw up another 10 cc's. Sorry, I'm just following my marker up there. There we are, that's just coming up to 10 there, and we squirt 10 more in down here. So now this current solution is now diluted by a factor of 100. And you see it's still so intense, the color, you still can't see through it. Now we take the next stage, we take up 10 more mils like this, you see, and we squirt this into here, and this is 10 cc's going to 90, and there we have a situation where we can now start to see through our solution. And then you see we now take this up and we take out another 10 cc's, and we're still, this is an amazingly, I'm sure you'll agree, remarkable color, intense color, that you can still see it so far down the line. So we've now diluted it by 10, 100, 1,000, 10,000, and now we're going to put another one in. So we're now diluting, this will be going to another 90 cc's. So this is now 100,000, and you can still just about discern the purple color. And then we can take it right through, and let's see whether we can still, so there's 10 cc's of there, have now gone into here. And at this stage, I think it would be, to say that I can see the pink would be an exaggeration, but we certainly know there is some there. So let's just have a look at a close-up and just ask ourselves exactly what we have in these flasks. This, you see, was 0.33 m. This was therefore this is 0.033 m. This is, okay, so this will be 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, minus 5, minus 6, minus 7. So this is a 10 millionth concentration. Now, Oscar, if we could just focus up on these colors, just to show them just these flasks closer up, so we can have a close up, that would be much appreciated. Thank you very much. Just focusing on these. So, Oscar is my assistant, and I thank him profusely for assisting me again today. So this, you see, this range of colors, dilution, I don't think you'll find many substances that can give you such a range of intensity of color for over such a long for so many states of dilution. But I thought, at this stage, it might be just out of curiosity, interesting to see whether I can say something about the actual number of permanganate ions in these. You see, the permanganate ion is the one which gives it the very intense purple color. Now, the Avogadro number, the total number of particles in 1 mole of any substance, is 6 times 10 to the 23rd. That number is completely intangible. I just can't visualize it. So I thought to myself, maybe if we can look at something that is tangible, then maybe we can express the number actually of permanganate ions in these solutions in some sort of tangible way. Now, something that is tangible to me is the population of the world. We all know we live on planet Earth, and I looked up the population of the world. It's about 8 billion. Now, 8 billion is 8 million. So that's the population of the world. Now, if we round that up, just call it 10 million, then we get the number of people on this planet as 10 to the 7. Now, if we have 10 to the 7, so I can talk as one population is 10 to the 7, one world population, that's our unit. Can we get at least a tangible number of populations into this number? Well, if you actually do the calculations, and I've done them and I'm not going to bore you with the detail, but the honest truth is this: if I now take 1 drop of this permanganate diluted to this extent and I let it fall like that, that's about 1/20th of 1 centimeter cube. That contains about 1,000 world populations. So there we are, 1,000 there we are. So that's just to give you an idea. At least it's a tangible amount. The number of permanganate ions in 1 drop of this is equivalent to 1,000 of our world populations today. How about that for an utterly useless fact? Nevertheless, I find these things interesting. Well, having shown you a little bit about the dilution of potassium permanganate and the intensity of the color, I thought I would turn a little bit to the chemistry of potassium, of manganese, in fact, to be a little bit more specific, to the chemistry of manganese. Now, a few years ago, my wife gave me a most unusual birthday present. She gave me this. Can I show it to you? I've got it over here. And there it is, you see. She gave me this, and I said, "Boss, what on earth is this? And what's it for?" And she said, look, you do all these experiments at school in test tubes and small flasks and everything, and the children at the back, they don't necessarily see all these small flasks and test tubes. So why don't you, since you do these demonstrations, why don't you have a proper large sized flask size flask to show them demonstrations and the people at the back can see? But I said, "Boss, I can't even fit this into my Triumph Herald. How am I going to go around with a flask this size?" She said, "Well, that's your problem, but I've given it to you." And do you know what? I found out that today will be the perfect opportunity to use this flask. So it's the launch of my this is a 12-litre flask, by the way. You can't get them any bigger than this. But I'm now going to hopefully show you some experiments using this flask and the permanganate ion. Now, why is this flask eminently suitable? Well, I hope you know why. It's because the permanganate has an amazingly intense color. And I'm going to now just put it aside, put these various bits and pieces aside, and move this flask into the foreground where you can see. Now, what I've got in this flask is 5 litres of water, to which I have added approximately 10 centimeters, 5 centimeters cubed of concentrated sulfuric acid. It's acidified. To put it in a nutshell, it's slightly acidified, and that will improve the effect of these experiments. Now, what I'm going to start off is obviously by making a dilute solution of the permanganate. Now, we've noticed that this one here is, I think you'll agree that this is a color which we can readily see. So I'm going to create this solution from here. Now, if I've got 5 liters in here, then just 5 centimeters cubed of this saturated solution of permanganate should give me a nice purple color. Excuse me, my syringe has fallen on the floor, so I'm just going to pick it up here, and very, very fortunately, miraculously, it hasn't cracked. This is a glass syringe. Now, this is a precise, oh, actually, silly me, it has cracked. The top up, but I can still just, do you know what? The end's broken off, so I won't be able to use it. Fortunately, though, I've got my plastic syringe here. This is slightly less accurate. If you don't mind, I'm just going to squirt down, but nevertheless, it will certainly do the trick. So I'm going to take out as accurate as I can. Now, this is, there we are, 5 centimeters cubed there of my potassium permanganate. This is the saturated solution, and we're going to squirt it in nice. There we are. So that's gone in now. That's pretty well 5 cc's. And now let us have a look and give it a little swirl around to see whether this solution has now acquired. Isn't that beautiful? So there we are, we have a beautiful solution, and I'm sure you'll agree, there's no point in holding it up to the camera because obviously this flask, you can see everything. And I just wanted to show you some of the chemistry of potassium permanganate, or the permanganate ion specifically, which is in here. But before I do that, I thought I would just introduce you just a tiny little bit to the chemistry which you're going to observe. And I wanted to tell you first of all that manganese is a metal element, and it's a member of a family of elements which are called the transition elements. And I have here a beautiful copy, colored copy of a periodic table. This is from a Polish school chemistry textbook. And if you can look at the elements in the middle, you'll see the yellow, that yellow block, those are the transition elements. Their transition elements have many characteristics which, in my opinion, make them the most exciting elements we can have. And I'm about to hopefully demonstrate some of this excitement to you. And I'm going to be doing it with respect to 2 of those elements. One of them is manganese and the other is iron. And in here, you see, I have some iron sulfate solution. This is iron 2 sulfate, again slightly acidified. And I'm going to add the iron sulfate solution to the potassium permanganate, or the permanganate ions. Now, I'm going to first of all add it and see if we can get a chemical reaction to occur. Now notice, the whole beauty of this large flask and with these experiments is to get experiments to occur which use very, very small amounts of chemicals. So what I'm going to do is add a very small amount, and that's the amazing thing about it. You don't need much to cause a dramatic effect. So I'm adding some of my iron 2 sulfate solution. There it is, just a tiny amount there. And as you see, nothing happens. But we'll give it a little swirl around now. Give it a little swirl around, and there you see, something is beginning to happen. Something is beginning to happen. Just add a little bit more. Another little squirt. And let's give it another little swirl around now. And now you see, the color is distinctly beginning to change to a reddish color. But now we give it another little squirt, another little dose there, another little swirl around, and now please watch happens. Absolutely amazing. You see, the dark purple color has completely disappeared. Now, why has this happened? Well, you see, a reaction has occurred now, which in the chemical terms we call a redox reaction. The permanganate ion, MnO4-, is a powerful oxidizing agent, and the manganese, this is the important thing, manganese has an oxidation number of +7. It's very, very combined. Iron 2+, though, is very, very easily oxidized to iron 3+. So what this does, this is what we call a redox reaction. The green color has been discharged, and the permanganate has gone from Mn plus 7 in the permanganate ion to Mn plus 2, which is a very, very pale pink colour. It's so pale pink, only concentrated solutions will show it. Now, what this colour is, this has now got the colour of Fe3+, the Fe3+ ion, which although you can barely see it, it's just a pale yellow colour. You can hardly see that pale yellow. However, transition metal ions also form what we know as called complex ions. And these are ions which are slightly more complicated, obviously. And I wanted to show you one of these by adding what I've got in here. Now, this is sodium thiocyanate solution. And this, you'll notice, should give a brilliant bright orange red colour. And the reason being, it will be reacting with the Fe3+ to make the complex ion thiocyanate. So watch as I add a little bit, and let's see whether we get this intense red. And there you see, it's already beginning to develop. There you have a tiny amount. Just look at that. Isn't that amazing? This is what we now call the iron thiocyanate complex ion. I haven't got the time to go into the details today of the shape of the ion or anything like that, but I just wanted to show you this is an extraordinary example of the splendid chemistry of transition elements, which I told you, I just think this is absolutely amazing. And do you think I'm going to stop there? No, I have another trick up my sleeve. In here, I have some sodium sulfide solution. Now, sodium sulfide contains the ion S2-. Now, this is a powerful reducing agent. What we've got in here, we've got iron 3+ thiocyanate, but we're now going to add sulfide ions, which will reduce the iron 3+ back to iron 2+. And as it does so, hopefully, we'll watch this red colour disappear. So let's now continue. Let's add some sodium sulfide and watch what happens now. A little sodium sulfide. Now, initially you see a tiny little bit of black around there, but that's due to and as we swirl it around, and what I can tell you is happening is that because this solution is acidic, it's reacting with sodium sulfide to release hydrogen sulfide inside the solution there. Hydrogen sulfide is an extremely toxic gas, and I'm doing this, by the way, a little bit at a time. A little bit at a time, and the reason being that I want you to see the changes gradually. Anyone can do things rapidly, and so, but the whole point is that you can observe the changes occurring. And now a little bit more sodium sulfide, there we are. And as I said, it's reacting with the sulfuric acid at the moment in there. It's an acidic solution, as I told you, and it is producing hydrogen sulfide gas, which is dissolved in the solution. But very shortly, the equilibrium will be disturbed. As we have an excess of the sulfide ions, they will start to reduce the Fe3+ to Fe2+. And this is what happens. Hydrogen sulfide is molecular, so it's not available, and you're seeing the colour is now distinctly beginning to fade. And as we add a bit more, we swirl it around more. Observe now what's happening. Gradually, the colour is getting fainter and fainter, and we're running out of sulfide, but that doesn't matter because I have a spare bottle should I run out. Please watch carefully. We've now almost now discharged the entire of our red colour of the thiocyanate complex. So what that means is we're now getting rid of our we're getting rid now of our, excuse me, I'm just going to get a little more. Oscar, could you kindly pass me that conical flask there? Thank you very much. That conical flask with a cork on it. It's a special there. That's it. Thank you so much indeed. Thank you very much. And as you notice, please watch carefully. We've now virtually got rid of the yellow colour. It's now gone almost white, and I will explain exactly what we've got. I'm doing this a little bit at a time because I want you to be able to observe. And there you see we have now a milky solution, a milky white solution. So you may say, well, how on earth, where does that come from? Well, I'll tell you, it's come from the redox reaction between sulfide, which has reduced Fe3+ to Fe2+, but at the same time, the the sulfide ion has been oxidized to elemental sulfur. So what you're looking at, that white milkiness in there, is in fact the element sulfur, which has been formed from the redox reaction between sulfide and Fe3+. Isn't that amazing? And now as I carry on adding more, do you think we're going to stop there? Look at that black. What on earth is that black stuff? Well, now you see we have a completely different type of reaction. We're now going on because you see iron 2+ reacts with the sulfide ions to make iron 2 sulfide, and that is a black solid which is totally insoluble in water. And there you see, just to show you, as I continue adding my sulfide, the black color will become more and more visible and more permanent, until indeed it will be the predominant color in our solution here. And there it is. I think we're there. So that now you see, and here it is. What a remarkable range of reactions. So we've seen redox chemistry, neutralization of acid with alkali, and we've also seen the formation of a precipitate of iron sulfide. So let's just have this here. There we are. There's our black. Now, just to summarize, I have actually, because I think these colors, I would like to decant them one at a time. Let's just do a recap then and explain once again the predominant colors. So that's permanganate, MnO4-, manganese in the +7 oxidation state, purple. The next one we had was the very, very pale yellow, Fe3+ there, and Mn2+, which has no color at all. The next one we had was the Fe3+ thiocyanate, a complex ion which we see here. And the next one along which we had was the sulfur, which predominates, Fe2+, very pale green. So there we have the sulfur from the reduction with sulfide. And finally, what we see, of course, in this flask is the iron sulfide, which is completely insoluble in water, and that explains the blackness of the precipitate. So then that's in just a little bit of what we call redox chemistry of potassium permanganate. But do you think I finished there? No, I have one more final trick to show you. I have been searching around because you see, one thing I do know about oxygen, and one thing I know about why potassium permanganate is used in pyrotechnic mixtures, is because it makes things burn much better. And the element which is necessary, of course, for combustion is, of course, oxygen. So what I'm going to do now is to show you an experiment where I will be using oxygen, I will be making oxygen from potassium permanganate, and I will be using that oxygen to make something burn better. Now, if you allow me, I'm going to get out my apparatus for this next experiment. And here is my little oxygen generator. Allow me to tell you how this works. I will be making the oxygen by using solid potassium permanganate, and I have a bottle of potassium per... Deary me. I keep knocking my syringes. It's all right, Oscar. I keep knocking things off. I'm sorry, it's very, very annoying, but fortunately, it hasn't done any more damage than could have already been done. What I've got in here is potassium permanganate. Now I'm going to take a tiny smidgen of this potassium permanganate and I'm going to place it into the bottom of my flask here. This is, by the way, a Buckner flask. It's used for the Buckner filtration. It's a beautiful piece of apparatus, and it's made of thick glass so that it can withstand vacuum. Usually they create vacuums in these things, so they're created. It's made with an extra thick glass wall. But today I'm not going to be creating a vacuum in it. I'm going to be making a slight pressure, actually no pressure at all, but I'm going to be making the gas, and the gas I'm going to be making is oxygen. Now, before I do this, I have to do a little tidying up because we don't want to accidentally knock over these beautiful glass flasks which I have here, and I'm going to be making oxygen from potassium permanganate, which I've told you about already, which I've put in here. And the other substance I'm going to be doing is hydrogen peroxide solution. Now you can buy hydrogen peroxide in the chemist. It's used as an antiseptic for treating minor problems. And so this is going to be my oxygen generator. By the way, I don't have any rubber tubing at home, so I've had to improvise, and this piece of plastic tubing is taken from my Triumph Herald. It's the radiator overflow pipe. So here it is in action doing something completely different. And I've attached to the end a little bit of a teat pipette. This is from a dropping pipette for nose drops. So I've improvised a little bit here, and I'm going to use a tap funnel which I found in my collection here, and I'm going to put it in on the top here. Now, I'm going to obviously set something on fire. I don't have any wooden splints, so I can't show you it relighting a burning splint, but that's something, a glowing splint, should I say, but that's something which you know, and then you won't be that impressed by in any case. But what I'm going to show you is I'm going to strike a match now, and this will introduce you to what I wanted to talk about now, the combustion of, and that is, here it is, you see. Why has that match caught fire? Well, because there is an oxidizing agent in the match head, and on the surface of the matchbox there is a coating which includes phosphorus sulfide, or indeed red phosphorus itself. Now, I'm very fortunate because in my collection of chemicals which I've been given at various stages of my career, I have here some red phosphorus. Now, phosphorus is a very, very interesting element. It's very flammable, and it exists normally in two forms. You can have either white phosphorus, which is very, very toxic and also extremely flammable, which I don't have any of today, or you can have red phosphorus, which is far less toxic. It certainly is flammable, but not so as to be dangerous. In fact, it's simply got the flammable sign on there, so it can easily catch fire. Now, I'm going to, therefore, set fire to some phosphorus. And I'm going to do so by placing a small quantity on my special, by the way, this is an ignition plate. It's where you test the substances which burn. It's again for laboratory use when people want to investigate how things burn. I have placed a small quantity of phosphorus on here, and I have my little splint here. Now, what I'm going to do is to pour into my funnel, my tap funnel here, I'm going to pour some 3% hydrogen peroxide solution. Now, this hydrogen peroxide solution will react with the permanganate to give pure oxygen, and the pure oxygen will be funneled out by my Triumph Herald overflow pipe, radiator overflow pipe. So allow me now to show you this reaction happening, and we can control it very carefully, by the way. We can control this reaction very carefully, and I'm going to turn the light off. Now, the fan we're keeping on, but we'll turn the light off in a second. And Oscar, I'm going to, Oscar, could you kindly, oh, sorry, turn this one off first. Sorry, this one off first, because I want to show everyone the oxygen being produced. So please watch carefully. I'm going to bring this right up closer to the camera, and I hope it's in focus here. And I'm going to allow some hydrogen peroxide to drip onto the potassium permanganate, where you should observe frothing. A huge amount of effervescence, as we call it using chemical terms, and there it's going down now, I can see, and very shortly, there you are. And you see that bubbling there? That bubbling there is giving off a huge amount of oxygen gas. Now, how do we know it's oxygen gas? Well, because if I had a splint, it would relight the splint, but if I play it onto my candle flame here, it might just make the flame glow a little bit better. But sometimes it blow, even though it's oxygen, it may blow the flame out, but it's sort of tending to go a little more. Let me demonstrate this oxygen by allowing the oxygen to flow onto a match which is burning, and hopefully they could see the match is burning brightly wherever the flame reaches it. Oscar, could we now please extinguish the light in the studio, and please allow me, I'm going to set the phosphorus on fire now. The phosphorus is now burning, and please watch carefully now as I give it pure oxygen to make it burn better. And there you see the look of amazement, as oxygen, I'm going to increase the flow rate of oxygen. This is just such fun. And this is a serious amount of oxygen. Just look at that flame which is now being produced, demonstrating once again the fantastic effect of oxygen on improving the combustion of an element. So our phosphorus is burning away there very rapidly. Can we have the lights back on, please, Oscar? Because now I'd like to show everyone what is being produced here. What is being produced in this experiment here is, of course, this dense white smoke. Thank you very much indeed. And that will carry on. We can let it carry on burning gently. As you see, my fume hood is extracting all the smoke. And you might think to yourself, well, what is this horrendous white smoke that's coming off? Well, it's, of course, phosphorus oxide. But you might like to know a little more about it. The chemical name for it is phosphorus pentoxide. Its empirical formula is P2O5, but the molecular formula is P4O10. Does this have any use in our life? Do we know anything? Of course it is. It is most useful. And explain to me why. Let me explain to you why. You see here, I have a bottle of Coca-Cola. Now this Coca-Cola, if you read the label, I'm sure many of you will know already, Coca-Cola contains phosphoric acid. And how is phosphoric acid made? Well, it is made by dissolving phosphorus pentoxide in water. So that, you see, is the acid anhydride of phosphoric acid, what we're producing here. And it's very useful because it's used, phosphoric acid, for making Coca-Cola among many other uses. Why is phosphorus important in any case in our food? Well, because our entire skeleton, our bones, have a significant proportion of calcium phosphate in them. So there you see a nice little link up of the materials which I have randomly lying around to give you a little bit of useful chemistry. And now just let me tell you a little bit about phosphorus. I can tell you virtually nothing actually, because I wanted to tell you a brilliant book has been written about phosphorus, and it's called The Shocking History of Phosphorus, a biography of the devil's element. Now, this was written by my good friend, the author John Emsley, who's an outstanding chemical author, and may I warmly recommend this book to you. It's eminently readable. You don't have to be a specialist chemist, but it tells you a lot about how phosphorus has played an amazing role in warfare, in agriculture, in medicine, and so forth, and also about its discovery. And I wanted to show you here a very, very famous painting. This is a reproduction of a famous painting by, I'm not sure who the man was, by Darby, that's right. He was an historical painter for scenes involving especially science experiments. And what he's drawn a picture of there, that man you see looking at absolute amazement at a flask which is glowing, that is the German alchemist Henning Brandt, who in Hamburg in 1669 for the first time made phosphorus. He made white phosphorus which was coating the inside of that flask, and therefore the flask was glowing because it was glowing as it was being oxidized by atmospheric oxygen. Now Henning Brandt thought he had actually made the philosopher's stone. He hadn't. He actually made it, by the way, by roasting together horse's urine with dung and with charcoal, and that's the result he got. Phosphorus, of course, as I've said, is very much abundant in animal and human bodies. So there you see, having shown you a little bit of the chemistry of the manganese, the chemistry of iron, a little bit of the chemistry of phosphorus, perhaps it would be prudent to return to our story of Shepherd's Bush Market, because that's the note I wanted to finish on. You see, a few years ago, in fact about 30 years ago, I was telling the story, in fact more than 30 years ago, I was telling the story of the Shepherd's Bush Market medicine man to a class of students. And one of the pupils, his name was Scott, he said, "Sir, my dad told me all about this man at Shepherd's Bush Market, and he used to go there and he used to see this magic medicine man as well." So I said, "Scott, that's absolutely amazing." So at least the whole class now knew that I was telling them a real story and not something I had just fabricated. So we then said, we mentioned this briefly, and the story sort of it lived in my mind, etc. But, and this is the amazing thing, a few years ago, just literally a couple of years ago, Scott contacted me again. He said he now lives in New York, he's married with children, and he said, look, Schindler, I've come to Highgate, and my dad is very keen to meet you because he really fondly remembers these days at Shepherd's Bush Market. So do you know what? Exactly 2 years ago in early June 2018, Scott's father came and we met outside the school. And here is the photograph of us together. You see me on the left hand side and Scott's father on the right hand side. And we had a fantastic conversation there discussing the road from Shepherd's Bush Market. Of course, as you could imagine, the whole thing was a contrived act. The whole story of the aspirin has nothing to do with the reaction at all, and nor indeed does the water. The permanganate, the glycerin, by the way, the cough syrup, that is a well-known spontaneous chemical process. So on that note then of our story from Shepherd's Bush Market, I bid you a very good afternoon.